I'm here with one of the co-founders of Databricks, Reynold Xin. Say that correct? Awesome.
Close enough.
And close. Look, we were just talking about my name and how difficult it can be, so I think we're even. Reynold, you want to go ahead and tell us a little bit as to why Lakebase matters so much to not just current Databricks customers, but why it really matters to the ecosystem as a whole?
Yeah, Josue. Hope I pronounce it
You
correctly.
said that. Couldn't have said it better myself.
Well, thanks for having me here. I think from a broader industry point of view, really, I was talking about this at Data and AI Summit. We felt like databases, OLTP databases, really haven't changed that much in the last 20, 30 years. If you look at analytical databases, they have evolved a lot. Like we are now probably 2 or 3 orders of magnitude faster than we were in the 90s and maybe even early 2000s. And there's a lot, that's because we built on a lot of foundational technologies that are both cloud-based and also just hardcore like database engineering. But OLTP database, more or less, if you crack open a MySQL, Postgres, or Oracle today, there are a lot of changes, but they look more or less the same as what they were back in the 90s. So we felt just that, hey, it's the right time to think about how we can disrupt and build next generational databases that are cloud native and also agent native. The one thing that was pretty interesting, we actually didn't know about this until the Neon acquisition, which was 80% of the databases on Neon was actually created or were created and managed by AI agents. And this is an incredible sort of stats because a year ago that number was 30%. So it went from 30% to like 80%. And if you just extrapolate that line, at some point 99% of the databases will be created by AI agents. And historically, databases were really operated, like provisioned and operated by humans. And I think with the LLM trend, agentic coding, we'll see that basically the actual persona, there might be still a human somewhere that's probably supervising all of these agents, but really the persona is changing from humans to agents. And that shift in persona, I think, comes with a lot of new requirements that historically simply weren't even part of the requirements list for databases, or maybe they were they're not even the top 100. An example would be, hey, you want to parallelize a lot of different agents to work on a task and maybe have each agent run some version of the experiment, and you want to compare which one does best. At this point, you want to be able to snapshot your data and then actually provide a different instance of the database that's fully isolated in a sandbox just for that one agent, because the agents could be making mistakes. You don't want the agent to be impacting your actual data. And every one of this operation would be pretty fast because the agents are operating at pretty fast speed. So I think there's just a lot of all these new requirements that are coming in now that which historically simply not even a concern for database system developers. And we love that when this new requirements come in, we think it actually gives an opportunity for us to rethink the fundamentals and think about how we should be architecting databases. Then we can build the databases for the future. So the databases of the past were built for human operators. In the future, will be built for human operators that are supervising a lot of different agents doing it. And it's also intellectually sort of challenging, but ultimately it comes down to, hey, we think we can build a new era of databases that's just much better than what was done in the past, especially given a new persona.
And I also think too, the agent side aside, obviously apps have been a big investment for Databricks too, and I think a very good opportunity of growth. So I
Yeah,
think you also have that going on for you. Agents aside, I know everything is agents right now, but I think even agents aside, I think having the ability to have everything together in one single place.
no, absolutely. Databricks apps has been the number one, I would say maybe it might have been the fastest growing product in the history of Databricks. It used to be Databricks SQL, but I think apps actually took that. Now it's earlier on, so maybe it's a little bit hard to predict exactly how it will go in the future, but it's been growing super fast. And the number one feedback we've been getting from customers is, hey, can I just get a provision database together with every app I provision? So we're definitely seeing that trend.
Yeah, no, and I just wanted to add that just because I think, yeah, again, there's so much in agents, and I know there's a lot of value going there. But for me personally, as someone um, that has dabbled back and forth in application development in the past, having so many of the pieces together, for me at least, it helps me actually get stuff done. So I appreciate that part.
The truth is, what's really good, a lot of the requirements for agents, once we actually can support them, it ends up being helping humans a lot also. But I would say for humans, it's a much nicer to have, whereas for a lot of the agents, it becomes kind of a necessity. But let's take like we talk about maybe creating snapshots and branches of your databases like quickly, right? That's actually an incredibly useful feature, even just for human coding. One of the things we see a lot of customers doing now is that they would, for every Git branch, it would automatically create a snapshot, like a branch of the data for the database. And developers really love it because it makes it much easier to test against high fidelity data.
Yeah. I know some of the founders tend to be more on the business side, some more towards the technical side. And I know you are definitely a lot more on the heavy technical side. So give us a little bit more details as to just how the architecture really works underneath the hood for Lakebase.
Yeah, so Lakebase has been building on this technology we actually acquired from Neon. And the interesting thing is we have been working together actually long before the acquisition. The and that actually led to the acquisition itself because we sort of just realized, hey, how great the tech was. And I think one of the big, like earlier we were talking about Lake so analytics database look very different today from like 20 years ago, and one of that change was Lakehouse. And Lakehouse has this one very important property, which is separate storage from compute. So you can store your data in massive volume in cloud object stores. This is like S3 or Azure Blob Store, and then you can launch compute instances that are ephemeral to be processing the data in the object stores. And there are many, many advantages here. One of them is it's just enable elastic scaling, right? You can dump as much data as possible, and then now you can put sort of when you have a big job to run, you launch more compute resources. When you don't, you shut them down. It's much more cost effective. And then the cloud object stores also tend to be probably the cheapest medium, durable storage medium for data. And the thing that the Neon team have pulled off and built, designed and built was that they actually they have a similar architecture, but it's actually harder to accomplish in OLTP because in analytics, 100 millisecond query is like considered pretty fast. But as a result, that tail latency spike of the object stores are fine. But in OLTP, you want to be able to process queries in less than a second or less than a millisecond. The second's way too slow. Like even 100 milliseconds often considered too slow. So the Neon, and the other thing is Postgres has kind of won and become the lingua franca of OLTP database. If you look at all the database usage trends, Stack Overflow, RDBM, DBMS ranking, Postgres like going up super fast.
In a thriving community too, right?
Yeah, community, large open source community. Like I think that's probably thanks to that large open source community, its usage and adoption is growing like crazy. But Postgres is not fundamentally is a coupled storage from compute instance. If you go pretty much to like vast majority of Postgres providers, they give you a box. The box has storage in them, has compute in them. You cannot independently scale it. If you need more storage, you now need more compute. And even that move itself is very difficult because it's more considered fixed capacity provisioning. So the Neon team actually figured out a really interesting way to implement separation of storage from compute for Postgres specifically. They built this storage service. There's actually two key services that sits on top of cloud object stores like S3. There's a safekeeper and there's a page server. The safekeeper is basically what it's think of it as a replicated write-ahead log. So the way databases work is instead of actually modifying the data in place, they write it to a write-ahead log first. And the safekeeper is basically a distributed replicated write-ahead log service. And the safekeeper is a service that takes all the actual Postgres pages. So databases, in the case of Postgres, separates all the storage into different sort of tiny granular small pages. The page server is a distributed storage system for all the pages. It ultimately stores everything in S3, but because we don't want to pay for the latency hit of going to the S3, it's a distributed farm that caches all the data also, as much of the data as we want, to provide much lower latency access. And then they make extremely minimum changes to Postgres to actually change the very underlying storage layer. They find some very narrow waste in Postgres. So you can change Postgres instead of writing to local disk for both write-ahead log and for the data pages. You just use these two services. They're on top of S3. And there's a lot of benefits that's make possible with this interesting architecture. One is the storage cost is super low, and storage is automatically durable. It's as durable as the cloud object storage, which are often either multi-AZ or multi-region. Whereas in the past, when you get a fixed capacity Postgres instance, that storage is only as durable as the storage on that box. So if that box goes away, you lose all data, right? So people then come up with storage like backup solutions, or sort of they may sell them like use EBS and like super expensive compared with S3. The other one is it makes it very super fast auto scaling, like on top of this architecture. The Neon team actually built an auto scaling service that basically provisions compute nodes, like Postgres nodes, in less than 500 milliseconds. And because you can do this now, I actually think it changes the paradigm of both for agents and for humans. Here, the agent's not just a marketing term here, but it changes the paradigm of databases. Because for many, I think while there are one class of databases that are extremely latency sensitive, and you simply cannot afford to have a tail latency spike at all, I think most applications, especially internal applications that a lot of enterprises build, it's okay every once in a while to have a latency spike of a few hundred milliseconds. You don't want it to be like seconds, but 100 milliseconds, fine. Right? Because that's roughly human perception time, 300 milliseconds. If we can actually provision and acquire compute resources in hundreds of milliseconds, now we can actually scale the database itself entirely down to zero without paying for it when there's no traffic to your service, which happens all the time also, right? Like you might have a lot of traffic for internal app in a specific time zone during 9 to 5, but then past that hours, it drops down to approximately zero for many companies. And for many companies, maybe the lunch hour is also dropping down, or maybe in some cases you have spikes at 9 a.m. because everybody like gets into work and start looking up some app. But then at 10 a.m., it goes down. It doesn't go down to zero, but it goes down. So they build this auto scaling architecture that makes the database itself can adjust and its resources dynamically based on the load, and can also go all the way down to zero. And this is super cool because I think it's actually probably the first time that you can have an OLTP database be so responsive and so elastic.
One of the comparisons that I've heard and read some people make is, well, isn't this similar to how Aurora works from AWS? So I'm curious to hear your thoughts on that.
Yeah, that's a great question. I think at the very high level, there are some similarities, especially if you think about, hey, Aurora also have some attempt at, Aurora might have been the most popular of separated storage from compute OLTP offering out there. But if you actually look deep enough and think about the technical problem harder, it's actually very, very different. And that leads to very different benefits for the end user also. And one of them is that Aurora was actually, I think because Aurora started many years ago, Aurora started more than a decade ago. And at the time, the object stores were much worse. So they had to build a completely proprietary storage engine that are not open at all, and only Aurora services would have access to. And whereas if you think about the Lakebase side and Neon, it's built on just Cloud Data Lake. It's built on S3, it's built on Azure Blob Store. And this might seem like, hey, what's a big deal? Like proprietary storage system, a more open storage system, what's the big deal? There's actually a massive difference here. One is, aside from the engineering, it's actually engineering wise more complicated to build it, to make it work for object stores. But what's the benefit? Why should maybe the user care? One is cloud object stores are far cheaper than EBS, just because the way it was done. EBS considered more of a high-end network attached storage, whereas cloud object store is more of a data lake. And data lake are fundamentally cheap. They just have much better unit economics. The second thing is, because it's built on cloud object stores, and the data that's stored on it are also open spec and open source. Like they're literally just Postgres pages. So we're kind of recreating the interesting lakehouse paradigm here, except for OLTP, which is you have the actual source of data stored in cloud object store, which can be very high throughput in open format. So on top of we could not just build, we're not just building OLTP database and Postgres being able to access that, but we can actually build, we haven't done all of it yet. All of this are still in the work, but it enables that possibility of having, for example, Spark directly querying all the data. Having sort of DuckDB querying the data, just provided there's a right adapter for it. But because it's open format, and it's honestly, it's just Postgres pages. We could be creating, either us or sort of the community could be creating those adapters. Yeah, so it just opens a lot of use cases. And I can give you an example of what it might be. Let's say, well, one very simple one is, hey, there used to be this giant divide between analytics. This is like Lakehouse, Data Warehouse, Data Lakes, and OLTP.
Yeah,
right.
OLAP versus OLTP.
Yeah, when you become Lakebase OLTP, when you become successful enough, you want to start applying analytics on OLTP data. How do you do that? You start trying to build pipelines to get data out, and you learn like complicated concepts like CDC and all of that. But if the actual OLTP data are open format on top of data lake, which is basically lake houses, now they're no different from a lakehouse data. Just go read them directly. You can read them using Spark. You can read them in massively parallel fashion. If you have a petabyte of data, go read them. It's not an issue. I think that just changes the scaling and also makes a lot of operations simpler. Every database, like every company operates, I think any large enterprises operates tens of thousands, if not millions of databases. They are destroying database instances because the storage was not shared. By having all of that storage in one data lake, basically the lakehouse here, you can now actually enable workloads that plumb through all of them. Like for example, if you want to identify, if you want to do a global scan, let's say hypothetically speaking, if you found so one of your database that got compromised, and there's a table that got created with a hey, send Bitcoin to this address, and I'll give you your data back. Right? Hopefully, in the case of Lakebase, you don't have to worry about getting your data back because we have like time travel and snapshot of them. But you, at the very least, you want to know, hey, what's going on with my other databases? Did anything else get compromised? How do you do that across maybe a million different instances if they are destroying? It's an incredibly difficult, time-consuming, laborious job. But if all of them are actually in the lakehouse, you could actually write a single Spark query to scan all of them, or in DB-SQL if you like SQL. That, I think, is going to be revolutionary to how we operate and manage databases as well. Okay, This is not like a super complicated demo. I just want to show maybe quickly the developer experience and how fast it is with Lakebase. And this is just your standard Databricks workspace UI. Any Databricks user should be pretty familiar with it. But there's this new thing here with a little bit drop down that goes into this thing called Lakebase. In Lakebase, you can create a new project, which is effectively a database with many different potential instances. Let's say host rate test. So I'm going to create a new one, maybe one here. So now we've created a new database project, and everything is super snappy, super fast. In this case, it automatically creates a development branch of the database also. And then if we just come in here, the primary basically the primary branch of this, or primary replica of this branch, production branch, is now available. And just want to run something. Some query here. It's like some sample queries it's running. And everything's completed, all the SQL queries. And it just took, it's fairly fast. But what is interesting is if you want, for example, to create a trial branch of this production, like my trial, and you could actually have it automatically disappear. So for example, if you know that you are only using this for less than a day, you could do it. But if you don't, it's even okay. And then you can create a branch based on whatever data is in your production branch. You can actually based on past data. I mean, we don't really have anything in the past. We just create it here. You can just create. And now that branch is created. And this branch is actually, it's effectively free because it has this copy on write architecture that unless you start adding more and more data to it, it doesn't really cost you anything. It only costs you when you need to use some compute against it, which hopefully is pretty short because you're using it for development. And it only costs you if you start writing additional data to it. But otherwise, you can have like, say, a terabyte of data in your production, and then you create a branch. The branch is copy on write, so it doesn't actually cost anything additional. But then you actually get all these branches for basically as separate independent branches. That each of them is kind of its own mini Postgres, but just at the storage layer, they were pointing back to the same storage. So this super powerful.
Quite literally, it's not that you are duplicating the data in itself, but you're
no
basically
data duplication at all.
Yeah, you're it's a logic. It's a logic level basically that's ultimately in a very simple way. It's a logic that's telling you, hey, these are the records that should belong here. These are the records that should belong in this other branch.
Yeah, exactly. And then because of, well, in this case, we're doing the auto scaling of 0 to 4. This is sort of approximately some sort of memory, sort of the hardware, but you could actually get it to like super small. You can have it to scale to 0. So if there's no usage after like 5 minutes, this whole thing just disappears. But then if it needs to come back, it will come back in hundreds of milliseconds.
So the compute is disappearing. You're still paying for the storage.
You're paying whatever you have in storage. If you have like
but the compute, you're not really paying anything more for compute in that moment.
And the storage is like super cheap.
Yeah. But yeah.
So this is basically the entire experience. It's super simple, and it's a full blown. We didn't really show it's a full blown Postgres. You could use the built-in SQL editor, but vast majority of the people will actually be connecting to it through probably from the applications, right?
This is the new and improved Lakebase.
Yeah. So it's a little bit confusing here. So we announced Lakebase public preview actually at Data and AI Summit. And that is more of a fixed provision Lakebase. So you provision whatever resources you want, and that's it. You could re-provision or provision it down. It would take a while because it's still separated storage from compute. It's the same Neon storage technology under the hood. But what I have shown here, this is an improved version upon that. That's in beta right now. that actually has based effectively all of Neon.com's technology. So it's not just the storage part, but the entire auto scaling, the developer experience, all of that. So that's when we now have like snapshotting, branching, backup restore, all of those are now, and everything's like super simple. It's just in the UI, or so you can use command line, all of that work. And it's much snappier. We actually see this to be the future, and eventually replace the current Lakebase, basic provision Lakebase.
It's kind of like a branch of Lakebase right now.
Yeah, exactly.
That's awesome. Thank you for that.